Hello everyone, welcome to CYBR601 Learning Activity 5 Lab, focused on numerical simulations. And to get this kicked off, before we jump into Anaconda, I'm going to actually show you where to go. So you may have downloaded it already. If so, feel free to fast forward a little bit past this installation video, because I'm going to take about 5 minutes to show you where everything's at and for Anaconda, and then show you where to go, and then of course on Canvas where to get the Python files. So let's go ahead and start off with you can go to just getting this Anaconda software downloaded. So if you haven't done it already, you're in great shape, because we're going to do it right now. So go to Google, and then the first thing you want to do for the Anaconda software package is type in Anaconda, and then what you'll do is Navigator download. That's perfect. So Anaconda Navigator download. And what you do, first link here, Anaconda distribution. And all right, so this actually works for Windows, also works for Mac, Apple, and also works for Linux installations. So you should be good either way. Go ahead and click download, and it's pretty short. You're gonna get this. You're gonna get a download process. And once that's completed, you'll get actually a whole suite of tools that are going to get downloaded with it. So I'm going to go ahead and let that run, and then once you have it downloaded, basically you'll just go to the folder and execute that. I've got Windows on my machine, so I'll do the install for that. But it's really straightforward. And same thing for Mac. You'll when you download it, just click it and it installs. Okay, so I'm gonna let that run, and then we're gonna jump on over to assuming that your installation went smoothly. I'm gonna go ahead and jump on over to the Anaconda framework. Okay. All right, so after that's installed, what you want to do is you'll get, you can type in, for me, this is on a Windows machine, you'll have this Anaconda Navigator app. So if you're on a Mac, you'll have to reach out if you're having trouble on a Mac, or if you have any issues. We can work with you on that. I don't have a separate Mac installation software, or rather video, but we do have Macs here. So if you need a hand, I've got some professors that can help you with that. Okay, so again, just reach out to any of us. We can help get you in the right direction. Okay, so on a Windows, go ahead and click on Anaconda. And that should come up here in just a second. You'll get a splash screen here that'll start to pop up. All right, so after that's done loading up, you're going to get this suite of software packages that are going to download with Anaconda Navigator. Anaconda Navigator by default will install a separate environment and a separate Python environment. So if you have Python already installed, there's a couple things you might want to just double check, and just make sure that all of these applications are using base root. If you have another environment that you want Python to run, again, this is if you want to get into the weeds. Then you'll come in here and you should have a different Python. You can select from a different environment rather. So, but go ahead and use. I would just use a default installation for everything, just to kind of keep it clean. Again, if you have run into any issues, reach out. We can get you squared away. All right. Let's go ahead and the next thing you need to do is launch Spider. That's this one right here. So go ahead and launch. And this will get us right to the 5-minute mark. Once this gets loaded up, Spider is a scientific Python development environment. That's what Spider stands for. It's a very popular, what we call an IDE, interactive development environment. And this gives us, it's a coding environment, same thing as Visual Studio or VS Code is another IDE. Jupyter is another one. For this particular numerical examples, we're going to use Spider. Okay, I'm gonna all right, we'll say okay to that, and I'm gonna change us over to course modules. So under course modules, I'm going to go to Canvas. Apologies, Canvas. Within Canvas, up to this point, everyone should be in good shape with their syllabus. They've got their discussions posted. I think everyone's got that taken care of. They've gotten through all of week 1's learning activity at this point. So once you've gotten through week 1 lab, you're good to start on the next set of labs. Because I'm recording this ahead of time, these are not green, but when I release this video, these will be green. So you'll be able to go out and check. I will not have quiz 1 released until later in the week. Probably be on the lookout. I'd say Thursday-ish. I'll have that quiz 1 released. And then you'll have plenty of time to kind of study up and review week 1 and week 2 materials up to that point. Quiz 1, just as a note, quiz 1 will be open until actually we'll stay open actually, but your due date will be January 29th. That's when you want to look to have that wrapped up by the 29th. I will build in some flexibility, so if you go into if you end up into the 30th or the 31st, it's not the end of the world. The quiz will stay open. You won't lose any points or anything. Just make sure you take it. Don't get too far behind on that. But that's kind of a suggested due date on that January 29th for quiz 1. Learning activity 5: numerical simulations, concepts and applications. Is what the lecture is, and then this video is the numerical simulations lab. So these you definitely want to make sure that you're up to that you have access to these and that everything's looking okay, or that it's green for you. Okay, with that, to complete our simulation, numerical simulations lab, head on over to Files, and then under Lab Materials, I've got Learning Activity 5, Deterministic Stochastic Example. That example that I talked about in the lecture, this is the code for that, and you can feel free to drop it in and run it. But we're going to focus on this N-body simulator for Learning Activity 5, and then but this is where you need to download this. So just go ahead and download. It's plain text, so the code that you're going to see here is going to pop up here. It'll just show like a notepad file. And to illustrate that, this is taking a while, so let's just go ahead and download it right there, and then we can go over here, and then wherever you download it, just make a note. You can say open with, and I'm not going to say, so we can say just once. I'm just going to show you here. So this is what it looks like in Notepad. Pretty straightforward. It's plain text. So we're gonna actually from wherever you download it, I'm gonna just leave this in the downloads folder here, and then let's head on over to Spider, and then what I'm gonna do is I'm gonna go File, Open. So this is just follow along. So I want you to be doing this as well. I don't want you to just be watching me do this. I actually want you to go through the process of downloading the program, installing the Anaconda software, and then opening Spider up, and then opening up the Python program. In this case, the the N-body numerical simulator for the lab. We'll open it up, and there we go. So I'm going to go ahead and talk through this this program and while it's running. So in this case, I've got I want to disclose right up front, this is one that I did not write. This is one that actually was put together by a gentleman by the name of Philip Mox, and out of Princeton. And it's actually a really cool, for the money, it's a really cool simulator for N-body. Now there's some downsides to it. You're not doing cosmological simulations, but for anything related to, kind of even introductory grad courses, this is actually pretty good. It works really well. So let me talk through this. There's actually, so we have some libraries. NumPy, what's interesting is there's only two libraries. It's Matplot and NumPy. That's all. Everything is, and NumPy is a numerical Python library. Matplot is a plotting library. And this is an N-body simulator using Python as its code base. And there are primarily three functions. There's an acceleration function. There's an energy function. So these are defined by these defs. These def get ACC. That's actually a function. So all this code here is related to this def. Or this function, and then there's another def right here for energy, and so all of these, so kinetic energy and potential energy, there's some variables that they're capturing here. Looks like they're doing some, looks like they've got some equations that they're writing up here. Nothing too crazy. So this is the energy energy function, and then this is the main, the def main function, and this is actually what's taking information, or rather, it's taking the acceleration function and the energy function and putting them to work together. Couple things that are going to jump out at you, and then let me go ahead and run this. I'm going to go ahead and execute it. So you go ahead and do this too. Go ahead and hit the play button. So I'm going to run this, and what it does is it creates a over here on the right hand side. It's going to create an animation. Let me there we go. And this animation is going to run. And actually what it's doing is it's creating a snapshot of images on each iteration. It's looping through this 4 in range, the simulation loop right here. So what it's doing right now is this is going to loop through n number of iterations, and it randomly put these bodies and set up a couple things. And I'm going to scroll back up here. A couple things that you may have noticed right up front. Remember in our lecture, we talked about a mathematically focused or a mathematically imbued numerical simulation that's physically informed. Well, this is it. So this is what's happening. But we also talked about, kind of on that information bucket for simulation architecture. We talked about simulation parameters and initial conditions for that simulation, and here you go. They're right here. So we've got they're generating initial conditions and then simulation parameters, and this is why I'm not too worried about us looking through the code, because I just want to spend a little bit of time talking through as this is going through its process here on the right hand side, and what will happen is this particular N-body simulation will start to show some particles flying off and zipping off, and then some particles starting to, or bodies rather, starting to aggregate towards its center, or starting to aggregate around a center. So we'll see it starting to do that here over time, but some just you see here on the right hand side, some have just already flown out of the system. Okay. So let's turn our attention back over to the code as that's starting to go through its dance, as it were. So simulation parameters, we set it to 50 particles, and you can play around with this. You can set this to 1,000 and see what happens. It's kind of cool. And then you can put t equals to 0, so that's current time in the simulation. Time at which the simulation ends is 10, and time step is 0.01. So in other words, between 0 and 10, it's 0.01 time steps. So you can actually do the math and determine how many time steps there are. And then you've got some other stuff like Newton's gravitational constant, switch on for plotting as the simulation goes along. So you can actually turn it off and turn this plotting so that, in other words, I believe what will end up happening is it just, it will plot the final end solution. So when time step equals 10.0, then plot real time actually, when it's set to false, will actually just show what the final solution looks like. And that's certainly a possibility. In other words, it's hiding the steps. So generate initial condition, random seed 17. Typically, you can play around with this random seed generator. It should not have a material impact on the end body simulation and how it behaves. It's think of it as kind of like in Minecraft or like a game. There's usually an initial seed condition that's set. It was made famous, or it's actually been around for a while, but it was made famous by No Man's Sky, the game NMS, and they had to reseed the entire universe, which caused all kinds of problems. So people that came in on the initial seed were given, you build up certain. You build up certain equipment, and you acquire certain functionality over time, and then when they reseeded the universe, stuff changed. Let's see. That's a seed, and then you've got total mass of particles. You can set the mass of the particles. Now that is going to have a material change, as well as this randomly selected positions and velocities. The positions and velocities, if you goof around with that, that's a what would we say based on the lecture? Is that a deterministic or stochastic? Is this a deterministic or a stochastic simulation? So I want you guys to think about that. I want the people here in class to be thinking about this in this aspect of what we're talking about here, and then what you can do is after this simulation ends, so it's getting close to time step 10, and so it's going through and it's plotting out. If memory serves, this is plotting out. This is potential energy versus kinetic energy, and then the energy total of the system should be plotted out. So it's getting close to being done. This line over here, when this line right here gets to the end, that's the end of the simulation. And let's talk through some concepts. As this pretty straightforward. I mean, less than 200 lines of code, and a good dozen of those are comments. So this is even more compact than it's pretty cool program. So let's talk through some concepts. So model, right? In this case, what is the model? And it's kind of given away in the right up front, which is in the comments. It says calculate the acceleration on each particle due to Newton's law, right? And Newton's gravitational constant, and we talked about that. See, so that's the end. KE, yeah. So kinetic energy, potential energy, and then the energy total in the system. So that finished, and you can see what ended up happening in the right hand side here. Just things circulated in the middle. Feel free to rerun this, but let me talk through a couple things here from the concepts and how this impacts what we're talking about. So the model is the particle. Particles are the models, and then in this case it's a point model. And then another part of the aspect of the model is the trajectories. Those vector trajectories that you see, these little lines, that's also a model. So you could arguably say that this is two models that make one, but yeah, it's okay. The point is a model, the line is a submodel, and then together it's a model, right? A parent object called a particle. And it is abiding by a gravitational mathematical equation. And again, that's something that we talked about in the lecture. And in this case, Newton's law of gravitation. So then that's in here too, and that's calculated. And then we took that, and then remember the other part of that modeling and simulation, right? The model by itself is one thing, but we should have a simulation, and that simulation is taking these models and iterating on them over time. And that's what the simulation does. And there's an engine. In this case, I'm running on my laptop. I'm running some computer hardware. I'm running an operating system, Windows. And then I'm running an M&S software. In this case, the M&S software is Spider with Python. Python is the language. Spider is the integrated development environment that is managing the simulation. So that's, in a nutshell, that's the architecture. Okay. And for that concludes our follow along lab. So that kind of wraps things up here. So I want everyone to kind of take this time before you head on over. Take some notes of everything that you've noticed, things that jumped out at you on the follow along lab. And then what I'm going to do is you're actually going to go to a separate lab. So when you head back over to Canvas, there's going to be another lab for Microsoft MakeCode. That is it'll be a really short lab because that's actually for you to try. And the reason that I want you to, again, back to the lecture, is I want you to be thinking about comparing and contrast what you saw on the follow along lab to what is going to be the you try lab, which is the Microsoft MakeCode. And again, it's block coding, so you don't have to be a programmer. But it's great. The Starfield generator that we're going to create is going to have some very marked differences between what you see here and what you see in the you try. So, and it's going to have implications for your simulation architecture, your final paper. Again, more to come on that, but that's why make sure that you're doing both the follow along and the you try, because those are going to make the quality of your simulation architecture paper, your final project, that much more robust. Okay, this is the end of the first lab, and then what we'll do is I'm going to head on over to the U-Try lab, and then I think that just about wraps up here. All right, we'll see you later.